Welcome to Spotlight on Antibodies, a podcast from BioIntron, where we bring you the latest antibody industry trends. I'm your host, Jovina Celestio, and this month in November, we'll highlight how non-canonical antibodies are reshaping immunotherapy, combination antibody therapies, and T-cell exhaustion. As viral threats continue to emerge and evolve, a new generation of antibody formats derived from scalable and resilient immunotherapies. A recent review describes how avian immunoglobulin Y, IgY, camelid nanobodies, VHH, and shark variable mu antigen receptors, VNARs, can exhibit unique structural and biophysical features that make them well-suited to neutralizing respiratory pathogens, particularly when delivered intranasally or via inhalable formulations. IgY antibodies, derived from the egg yolks of immunized birds, represent a scalable and ethical alternative to mammalian IgG. Unlike IgG, IgY lacks the Fc region that binds mammalian Fc receptors, or activates complement, making it less inflammatory. Structurally, IgY demonstrates great thermal and protease stability. Secondly, camelid-derived nanobodies, or VHH, are the smallest naturally occurring antibody fragments capable of antigen binding. Their small size, monomeric structure, and extended complementarity determining region 3, CDR3, allow them to access cryptic or recessed viral epitopes that are often hidden from conventional antibodies. These properties have enabled nanobodies to neutralize a broad spectrum of respiratory viruses. VHH constructs targeting the hemagglutinin HA stem of influenza virus have demonstrated cross-subtype protection. Against SARS-CoV-2, engineered multivalent or biparatopic nanobodies have blocked receptor binding and destabilized the spike trimer, with potent activity across variants including Omicron. Importantly, their resilience under heat, pH extremes, and aerosolization makes them ideal for nasal or inhaled delivery. A recent review highlights the wide range of engineering options for nanobody optimization. VHH antibodies can be multimerized for avidity, humanized for reduced immunogenicity, or fused with effector domains to elicit desired pharmacokinetics or immune functions. According to structural analyses, VHH antibodies tolerate extensive framework grafting and loop mutations, supporting their use in modular or bispecific formats. The third format we'll talk about are shark-derived VNARs. The smallest known antigen binding domains exhibit exceptional stability and binding versatility. They are made up of a single variable domain stabilized by inter-CDR disulfide bonds, which allows for recognition of highly conserved, often recessed viral epitopes. VNARs have demonstrated promising preclinical efficacy against influenza and SARS-CoV-2. For instance, VNARs targeting the influenza M2 ion channel retained neutralizing activity even in amantadine-resistant strains. Recent studies have identified VNARs capable of cross-neutralizing SARS-CoV-1, SARS-CoV-2 variants, and other zoonotic coronaviruses by targeting conserved regions outside the ACE2 binding site. Engineered Fc fusion VNARs delivered intranasally also significantly reduced lung viral loads in infected mice. The modularity of nanobodies and VNARs supports the development of multivalent, bispecific, or trispecific constructs that can simultaneously target different viral epitopes. This engineering flexibility is critical in the face of viral antigenic drift, as seen with SARS-CoV-2 and influenza. By engaging multiple conserved epitopes, these constructs reduce the likelihood of immune escape. The unique properties of IgY, nanobodies, and VNARs justify their inclusion in pandemic preparedness frameworks and broader antiviral portfolios. Let's move on to the topic of combination therapies. Monoclonal antibodies have become increasingly important in clinical oncology, infectious disease, and neurodegeneration. Combination antibody therapies have been picked up to overcome limitations in monotherapy, such as resistance and lower efficacy. Monoclonal antibodies can block growth signals, induce antibody-dependent cellular cytotoxicity, or inhibit angiogenesis. Combining them allows for targeting distinct tumorigenic pathways. Preclinical and clinical studies support additive or synergistic benefits in select combinations. The well-documented success of trastuzumab plus pertuzumab in HER2-positive breast cancer and nivolumab plus ipilimumab in melanoma exemplifies the potential of rational combinations. Besides monoclonal combinations, recent advances in antibody-drug conjugates, or ADCs, are expanding the pharmacological repertoire. Combining ADCs with chemotherapeutics, molecular inhibitors, or immune checkpoint inhibitors has demonstrated promising efficacy in hematologic and solid tumors. For instance, enfortumab vedotin combined with pembrolizumab received FDA breakthrough designation for urothelial cancer, highlighting the translational potential of ADC combinations. Yet, these strategies must navigate overlapping toxicities and biological complexity, especially in solid tumors where antigen heterogeneity can compromise efficacy. Predictive biomarkers and ADC design, accounting for drug-to-antibody ratio and bystander effects, are critical to success. Here are some examples of antibody-based combination therapies. In oncology, antibody-drug conjugates are gaining serious momentum. By pairing ADCs with immune modulators or pathway inhibitors, early studies are showing higher response rates and longer progression-free survival in cancers like HER2-positive and triple-negative breast cancer, urothelial carcinoma, and lymphomas. ADCs combined with checkpoint inhibitors look especially promising, and researchers are even starting to explore ADCs with CAR-T therapies. In infectious disease, particularly COVID-19 in immunocompromised patients, monotherapy often isn't enough to clear the virus. That's why early combined therapy, using neutralizing antibodies alongside direct-acting antivirals, is becoming more common. This dual-target approach attacks the virus at multiple stages and shows better viral clearance and survival rates, even though it's not yet formal standard of care. And in Alzheimer's disease, anti-amyloid antibodies like lecanemab and donanemab have opened the door to disease-modifying treatments, but they're just one piece of a very complex puzzle. Researchers are now studying combinations that also target tau pathology, neuroinflammation, or synaptic function. Timing matters. Some add-on therapies may work best after several months of treatment. Of course, none of this is simple. Ongoing research and clinical trials will be crucial in refining these therapies and ensuring their long-term success in this high-risk population. Moving on, we're digging into one of the most important and most complicated topics in modern cancer immunotherapy: T-cell exhaustion, and how the newest antibody technologies are trying to overcome it. T-cell exhaustion is basically what happens when T-cells experience persistent antigen exposure and a hostile, chronic inflammatory environment. Over time, they lose their punch, reduced effector function, increased inhibitory receptor expression, and that puts the brakes on treatments like checkpoint inhibitors and bispecific antibodies. We know exhaustion undermines therapy, but the biological pathways that drive T-cells from functional to dysfunctional are still only partially understood. One major contributor is the upregulation of co-inhibitory receptors like PD-1, CTLA-4, LAG-3, TIM-3, and TIGIT. These receptors each suppress T-cell activity through different molecular routes. Checkpoint inhibitors have shown that blocking these pathways can revive exhausted T cells, at least partially, but the reality is more complex. Reversing exhaustion isn't as simple as flipping a switch, which is why researchers are turning to more sophisticated antibody approaches. And that brings us to the rising role of bispecific antibodies. By simultaneously targeting a tumor antigen and engaging the T cell, bispecifics can create much stronger immune synapses. But the new thinking is, what if we combine that physical engagement with the strategic disruption of exhausted pathways? Pairing bispecific antibodies with checkpoint blockade could boost specificity and synergy, pushing T cells to kill while also freeing them from suppressive signals. A brand new paper takes this a step further with nanobites, nano-sized drug-loaded bispecific T-cell engagers. These molecules target CD19 on tumor cells and CD3 on T cells, like a traditional bispecific, but with an added payload: an A2A receptor antagonist that blocks adenosine-mediated immunosuppression directly in the tumor microenvironment. Adenosine is a major driver of exhaustion. It boosts PD-1, CTLA-4, and LAG-3 expression, so shutting that pathway down locally can make a big difference. And in preclinical models, these nanobites dramatically outperformed standard bispecifics like blinatumomab. They improved T-cell function, reduced exhaustion markers, and produced stronger tumor control in vivo. It's an elegant example of combining cellular targeting with immunometabolic reprogramming, giving T cells both direction and support. Now, if we zoom in on specific tumor types, lung cancer is a great example of how complex T-cell exhaustion can get. Patients with lung cancer often show elevated expression of multiple inhibitory receptors, not just PD-1, meaning single-agent checkpoint blockade isn't enough. In fact, resistance to PD-1 inhibitors is frequently paired with increased TIM3 and LAG-3 expression. So, emerging strategies involve layering antibodies, some that block co-inhibitory receptors, others that stimulate T-cell activation. And ideally, these combinations are guided by molecular profiling, so physicians know which exhaustion pathways are dominant in each patient. But even defining what exhaustion means is still a work in progress. A recent article brought together 18 experts who all described exhaustion slightly differently, from complete loss of effector function to an adaptive state that protects tissue from immunopathology, to something that varies depending on whether the context is cancer or chronic infection. One key distinction they emphasize is between terminally exhausted T cells, which are TCF1 negative and largely non-recoverable, and the progenitor exhausted population, the TCF1 positive cells that seem to have stem-like properties. These progenitor cells self-renew and give rise to the terminally exhausted cells, but their developmental lineage is still being worked out. There's also growing evidence that the transcription factor TOX plays a major role in enforcing the epigenetic program of exhaustion, and scientists are asking whether these epigenetic marks can be reversed and what that might mean for the longevity of T-cell responses. And that's all for this month's Antibody Industry Trends. To learn more insights into antibody drug news, make sure to follow BioIntron on LinkedIn or our website at www.biointron.com. Keep up to date with further episodes from Spotlight on Antibodies by following this podcast.